5.1. We have 5.1 and we're doing exponential functions. If you know what exponential, we have properties of exponents, we have logarithms, we have all the great stuff. So first, exponential functions. Function f with base a is noted like this. So if we have the function f, so that's my function f, with a base a like this. So this is where the parent function of every graph is going to look a little different. So different type of parent functions, it's always going to have a different base, but just has one x. So like this would be a parent function with base 5. This would be a parent function with base 1/2. So as long as a is greater than 0, so again, this a value, because if this is negative, that's a transformation, and we'll get into what these two different graphs are, like this here. Now we're going to graph both of these on the same graph. So I'm going to do a table. You could also do this in your graphing calculator, but let's say if I plug in -2, -1, 0, 1, 2 into the equation. Again, you should be able to do this in your brain. 2 raised to the -2 power is going to give you 1/4. 2 raised to the -1 power is going to give me 1/2. 2 raised to the 0 power is 1. 2 to the first is 2, and 2 squared is 4. Now, if I do that same thing with my 4s, I would get 1/16, 1/4, 1, 4, and 16. So now I'm going to plot all these points. I'm going to do them in different colors so you can clearly see. So both of these are growth exponential functions. Now, if you look at this, they both pass through this point at 0, 1. So a lot of times if I talk about that point, that's what I'm talking about. The transformations like we have dealt with for every single one kind of the same transformations for these. One thing that you might not be able to clearly see, but this has an asymptote. That asymptote is at 0. Why is it at 0? Is because there's no number that we can plug into this that will give us a negative. Because when we plug in negatives, that gives us a smaller fraction. So it's never going to cross this. So both of these parent functions have an asymptote at y equals 0. So that's our horizontal asymptote at y equals 0. So right now I want you to pause the video and I want you to do this in your calculator or on your own. So notice how that negative just flipped these numbers. So when we have that negative inside the parent function with the x value, then that's going to be a flip or reflect over the y-axis. Again, if it was negative inside, maybe you know that that would flip over the x-axis. So this is reviewing transformations of functions. Now, when we're talking about exponential functions, we have a one-to-one property. Meaning if I can get my bases the same, then that means that it's going to have the same exponent. Example, if I had 3x is equal to 3 to the 7th, because my bases are the same, that means these exponent values has to be the same. So in this scenario, x would have to be equal to 7. That's the only option I have. So when we're using this one-to-one property, we always want to try to rewrite this so that the bases can be the same. So example, I can rewrite 9 as 3 squared. And then I have 3 raised to the x plus 1. Well, now because the bases are the same, we know that 2 will be equal to x plus 1. So if I'm solving for x, subtract the 1, I would get the 1 is equal to x. So same type of thing here. I want to rewrite this. Now, in this case, my base here is going to be 2. I can rewrite this because if I have a 1/2, that's the same thing as 2 to the -1. And I still have that x there. 1/2 is the same thing as 2 to the -1. If I rewrite 8, that is 2 to the 3rd. So now I have that -1x is equal to 3, so x would be equal to -3. I want you to pause the video and try to do these next two by yourself. You should have gotten that x is equal to 2 and x is equal to 3. Now we have transformations of our graphs when we have that base function. Again, the base function is always going to be different, so that's not a transformation. So when I'm doing this, a lot of times we already have certain numbers that we should know. So again, the A, the B, the H, the K, that is all transformations that we already have dealing with. So if this A right here was negative, that would be a flip over the x-axis. If it's greater than 1, that would be a stretch, a vertical stretch. If it's less than 1, it would be a vertical compression. Again, this is review. B is on the inside of that parent function, so it's like the B value, if it has a negative, that would be a reflection over the y-axis. If it is less than 1, that would be a stretch, a horizontal stretch. If it's greater than 1, it would be a horizontal compression. This moves it left and right. This would move it up and down. So again, here's my horizontal shift vertical shift. These are just examples, reflection and reflection. So when I'm looking at this, the first step I should always do is to look at what my base value is. So right here, I always tell people to box in your base because the 3 is not a transformation. The 3 is part of the parent function. So now I just have the subtract 5. That's on the inside of the parent function. So that one's always opposite. That's like that H. So in this case, this is going to move it right 5 because remember, that's always opposite. Again, here's my base. This is the outside of the parent function. This is going to move it up and down. So what we're actually moving up here is going to move up 6. This is going to move that horizontal asymptote up 6. So we're talking what's moving. This would move that point 0, 1 to the right 5. So right here, here's my parent function. Try to pause the video and try to do that one by yourself. You're also going to do this one, but you can rewrite this as 2 to the third. So that's where that 3 comes from, because I multiply 3 times -1. So how does this transform? So this has a reflect over the x-axis. This moves it to the left 7. Now this has a reflect over the y-axis. So that either one you could choose. Now, if you didn't rewrite this and you only had this answer on a test or quiz, I would still accept it. But it also has a horizontal compression when we rewrite the base. Okay, natural base E. So when we have this number, we have a base E. So if you look at your graphing calculator, you have this right here, this natural log. That's what we're talking about, natural log. Here's my base E. So if I push second base E and I raise it to the first power. So E is going to be a continuing number that goes on forever, 2.7, and it does not repeat. Even though it looks like it might repeat, it does not repeat. So E is that number, kind of like pi. And when we have this natural base E, so E raised to the x, we use that when we're doing continuously compounding interest. So here are 2 options when we are having an interest compounded. So we either can be continually, and that would be a PERT, where P is the amount of money that you start with, R is the amount of money of the rate that's given, and N, when you're talking about compounding, is how often you are compounding it. Like for this first one, quarterly means that my N is going to be equal to 4. And I'm using the same information for all of them. So this, how much money I'm starting with, is my P. My rate, you have to change this to a decimal, so 0.03. And my T here would be equal to 5. So right here, if I'm using this equation, it would be 12,000, and I have 1 plus, my rate is 0.03. I have to divide it by how many times I'm compounding the interest, and then I multiply that same number over here. If I plug that into my calculator, you would get 13,934.21 cents. Right now, I want you to try monthly and continuously. Continuously will be using this format by yourself. You should get 13,939.4 because the more often you accrue interest, the more money you'll have over time. And continuously would be like every single day. So obviously this will give you the most. So right now you should pause the video and read this if you haven't read it yet. Now when I'm looking at this, here's my equation. This is the big one. It's saying that there is this plutonium chemical in this time. That was the Soviet Union. So it's asking how much plutonium is going to still be there after 2017. So first we have to figure out what number would 217 represent. So if it happened in 1986, we can take 2017 and subtract off the 1986 because we're looking for what year would that be equal to. 2017 minus 1986, and we get 31. So after 31 years. So right now, I want you to pause the video and put 31 into this equation to see what you get. You get 9.991 pounds, meaning after 31 years, there's still quite a bit of plutonium in this city because we started off with 10 pounds, and then after 10 years, there's quite a bit. So still not able to live there. So same type of thing, but now if you plug 100,000 into that equation, what would you get? So do that right now. So after 100,000 years, there will be 0.564 pounds left of plutonium in that city. So 100,000 years, people maybe could start living there again. And that's all we have, folks. Have a great, have a wonderful day.